Ini dari semester 2 sampai semester atas yang sedang tugas akhir yang uh, diwajibkan untuk hadir pada kegiatan MRT hari ini. Puji syukur pada Tuhan Yang Maha Kuasa karena kita diberikan kesempatan untuk berhadir atau bertemu dalam kegiatan ilmiah reguler Prodi Kimia yang diberi nama MRT atau Monthly Research. Dan pembicara kita hari ini adalah Prof. Sumaiya. Beliau adalah Profesor Teknik Kimia yang luar biasa dan sepertinya CV-nya sudah saya serahkan ke Prof. Rainer. Mudah-mudahan sudah di tangan Pak Moderator untuk nantinya mungkin di uh, describe atau dideskripsikan sedikit atau sedikit detail terkait profil daripada Prof. Sumaiya. Jadi Prof. Sumaiya yang kami hormati bahwa setiap bulan kami melaksanakan kegiatan ini, selain karena memang kami kepingin tahu tentang perkembangan riset ilmu kimia dari berbagai pembicara di berbagai tempat, kami juga ini adalah bagian dari strategi untuk kami boleh mempersiapkan akreditasi kami. Puji Tuhan, waktu kami pulang dari Malaysia dan kami berproses dalam kegiatan akreditasi, kami mendapatkan akreditasi unggul, Prof. Sumaya, di
Alhamdulillah.
Badan Akreditasi Nasional di Indonesia. Oleh karena itu, kami berharap bahwa kehadiran Prof. Sumaya pagi ini bisa memberikan warna tersendiri terkait riset Prof. Sumaya di UMPSA dan mudah-mudahan ada mahasiswa kami yang bisa menjadikannya sebagai sumber inspirasi, bukan hanya mahasiswa tetapi dosen juga, siapa tahu berjodoh ya, dan ada yang mau melanjutkan studi di UMPSA. Saya pikir sangat terbuka karena saya sudah sampai ke sana dan saya sudah tahu bagaimana fasilitas di sana itu luar biasa. Oke, saya pikir waktunya kita juga sangat pendek karena Prof. Sumaya ada kegiatan lain di pukul 9, sehingga saya tidak memperpanjang lagi sambutan saya. Yang pasti bahwa saya mengucapkan terima kasih kepada Prof. Sumaya yang bersedia menjadi narasumber pada pagi hari ini, Prof. Rainer yang mempersiapkan acara ini dengan baik, Ibu Shirley, Bapak Ibu dosen, dan juga moderator kita, Pak Mesak, dan juga Bapak, Ibu, adik-adik yang hadir pada pagi hari ini. Dengan mengucapkan syukur kepada Tuhan Yang Maha Kuasa, saya membuka dengan resmi kegiatan MRT Prodi Kimia bulan Maret tahun 2025. Terima kasih, Tuhan memberkati kita semua.
Baik, terima kasih Prof. Febri untuk sambutannya. Selanjutnya, Bapak, Ibu, dan adik-adik sekalian, saya akan memperkenalkan Prof. Sumaya hari ini sebagai pembicara utama kita. Beliau merupakan seorang dosen, peneliti sekaligus dekan di Faculty of Chemical and Process Engineering Technology, University Malaysia Pahang, Al Sultan Abdullah, dengan kualifikasi pendidikan menyelesaikan Bachelor of Engineering dengan fokusnya pada Chemical Engineering tahun 2004 di University Putra Malaysia dan melanjutkan studi di S2 dan menyelesaikannya dengan gelar Master of Science dengan fokus di bidang Chemical Engineering di tahun 2006 di University Putra Malaysia serta berhasil menyelesaikan uh, studi doktoralnya dengan bidang studi Chemical Engineering di tahun 2012 di Loughborough University, Leicestershire, United Kingdom. Beliau juga merupakan ahli di bidang Reaction Engineering and Catalysis, Advanced Material, kemudian Renewable and Sustainable Energy, serta Separation and Engineering. Prof. Sumaiya Zainal Abidin. Terima kasih Prof. sudah bergabung bersama kami. Saya tidak memperpanjang kata lagi. Kepada Prof. Sumaiya, saya persilahkan waktu dan tempat. Terima kasih.
Ini boleh dengar suara saya?
Terdengar dengan jelas.
Bisa didengar, Bu, terdengar.
Terdengar.
Bisa terdengar, Prof.
Okey, saya share skrin dahulu. Sekejap ya. Hmm.
Recording in progress.
Sambil
Okey.
siap, Prof.
Okey, terima kasih buat Pak Misak, doktor-doktor, ibu-ibu, bapak-bapak, Ibu Febri,
Ya, halo.
semua dosen-dosen Undana dan juga seluruh warga Undana sekalian. Terima kasih kerana mengundang saya pada hari ini untuk berbicara berkenaan dengan topik riset saya. Saya seperti yang dimaklumkan adalah dosen daripada Fakultas Teknik Kimia di UMPSA, Universiti Malaysia Pahang Al Sultan Abdullah. This is currently my 13 years in UMPSA. This is my first lecturer academician positions that I hold, and I'm sticking to the university until now. Alhamdulillah, still in here in Pahang. I would like to welcome everyone to Pahang. Bu Febri dan juga team member sudah datang ke Pahang tempoh hari. Saya juga mengundang yang lain-lain untuk datang bersama-sama untuk berkolaborasi sama ada dari segi akademik ataupun daripada segi research pendidikan ya. Currently, I'm holding the position of Dean for the faculty. InsyaAllah, I think more collaboration will be done with Undana, especially from teknik sains dan teknik, Fakultas Sains dan Teknik, dan semoga hubungan rapat antara dua institusi ini akan berterusan sehingga even though if I'm not the dean anymore, we'll still keep in touch and we'll still collaborating on all aspects in academia world. Okay. So without further ado, I'm actually need to leave by 9. I'm hoping that I can finish everything by then. Sorry. Where is it? Okay. So this is a bit on my introduction. Today I'll be talking about optimizations of syngas productions via methane bioreforming using a promoted CuMnO2 catalyst. Actually, in our university or in our faculty itself, we have 7 clusters, and I am from the reaction engineering and process intensification cluster. So my work previously I'm doing more of my PhD in biodiesel itself. I'm producing biodiesel from exchange resin as the catalyst. And currently, when I came back from my PhD, my research was centered on the production of hydrogen from various sources, especially the thermochemical routes, such as reforming, gasification, pyrolysis, and some of the electrocatalyst, photocatalyst processes on producing H2, which is hydrogen. Okay, so for today's lecture, I'm going to focus on one of my current research. I'm doing the methane bioreforming, and we are developing catalysts to actually improve the process. So this is some of my introductions that or the outline of my presentation to like the problem statement. we are currently relying on the natural sources, and everyone in the world are looking for alternatives to solve the problems of greenhouse gases. And one of the options that we do have definitely is on the production of renewable energy. Okay, so specifically on methane, one of the greenhouse gases, we know that it's actually contributing to many problems in the world: the greenhouse emissions, the global warming, climate changes, health problem, and damage crop that make this gas need to be transformed to another potential energy that can be used in the future. So there comes this syngas. What is syngas? Syngas is a mixture of hydrogen and carbon monoxide, where this syngas production is actually being produced via gasification, pyrolysis, and a reforming process. And later it can be used to produce a chemical, synthetic fuels, power generation, and fertilizer. So in my research group, we are focusing also on the post-productions of SAF, which is synthetic aviation fuel, that can be used or can be produced from syngas itself. So there are quite a number of fruit that we are able to use to produce syngas or to produce SAF. One of them is from the syngas itself. So we are actually looking at cradle to grave processes, whereby via the, normally we are using biomass as a feedstock, and then we are converting it to syngas or hydrogen-rich gases. And further, we are trying to actually utilize it until it produces something that can be used, because hydrogen is an energy source. It cannot be used. It needs to be transformed to another form of material so that can be used later as an end product. Yeah, that's why we are focusing also on the post-productions of product via the syngas. So what is bioreforming? First of all, what is reforming? Reforming is you are transforming different types of hydrocarbon to become two things, which is carbon monoxide and hydrogen that can be used as a syngas. So there is a lot of reforming available. You can reform toluene, you can reform glycerol, you can reform any biomass, you can reform ethanol, so many things, and so many hydrocarbons can be reformed. But today I'm going to focus on methane. Why? Because as I mentioned before, there are so many disadvantages as we want to release methane to the environment. That's why here comes the bioreforming of methane. Normally, methane can do quite a number of reforming. We can have steam reforming, we can have dry reforming, we can have bioreforming, aqueous phase reforming, we can have dry reforming. And every single process that we have, they're actually producing the same thing, syngas. But the ratio between the hydrogen and the carbon monoxides actually determine what would be the suitable application for post-productions of product after the reforming itself. That's why people are playing around with the agent that's being used to reform, such as for bioreforming, you have two, either steams and dry. Dry is by using CO2. Yeah. So we are having CO2 as one of our potential. They are missing. They are actually putting a different equation here. I'm sorry, my student prepared the PowerPoint. At least CH4 plus CO2 to produce CO and H2. Okay. So by reforming, this is the equation whereby you have H2O, you have CO2, and you have methane itself, whereby this one is being catalyzed at high temperature, ambient pressure will be 1 atm, very high temperature, it up to 700 to 1000 degrees Celsius, and it producing CO and H2. Okay, there's quite a number of side reactions involved in bioreforming itself, and these are the reactions I have put here, like 6 types of reaction that can be used in bioreforming. Okay. So for our problem statement, normally when you have this kind of process, the one that determines the production yield and selectivity of hydrogen and CO will be the process condition and the catalyst. Okay, so we are trying to see the problem now with the current catalyst that being used was the catalyst synthesis, the metal that being used being sintered through the process where it agglomerates and it decreases the surface area. The second one would be the deposition of carbon, because we are burning hydrocarbon, methane, toluene, ethanol, ethane. So when you are burning hydrocarbons, you are actually forming coke on top of the surface of the catalyst. So it makes the activity of the catalyst very low. The stability is very low. And the selectivity of the product is very low. So what we intend to do in this research work is we want to actually lift up the carbon. We want to actually the catalyst able to self-lift the carbon from the surface of the catalyst during the reactions, and with the aid of the agent that we use. Now, currently, we are using steam and CO2. Yeah. So the catalyst that would try that we would like to have to explore in the study is copper, because normally in reforming, the catalyst that normally being used would be nickel, cobalt, but very rare studies has been done on copper, even though they are coming from the same family. They are coming from transition metal catalyst, right? So we would like to know what would be the impact of using copper in our study. And this study is being optimized by design expert, RSM. Yeah. So this is the objective of our study. We want to synthesize the CO-based catalyst. We are using ultrasonic wet impregnation. It's a normal wet impregnation method. You impregnate the catalyst, but you are doing it in ultrasonic condition, so that the dispersion of the active site will be much more better. We have tried this method like since we did studies on glycerol reforming, other types of reforming, and it was proven that the sonification is actually improving the dispersion of the metal, making the catalyst to be better in terms of the performance. Later, we are going to characterize the catalyst with various characterization techniques. And a second, we are going to actually optimize the process so that we don't waste so much time testing one factor at a time. We are trying it in as a whole using design expert, using response surface methodology, so we could actually minimize the time to get the maximum yield and selectivity. Okay. A bit on the methodology of the process. Here are the things that we have carried out. We have prepared the catalyst via the ultrasonic impregnation method. We characterize the catalyst. So these are some of the characterization study. We have did some other characterization as well, but in this study we only focus on this 4, where XRD you will able to know the crystalline phase, the size, crystallite size. You can know the phase of the compound presence. You can also see whether it's actually having an amorphous or non-amorphous catalyst. Second is on the BET. You want to see the surface area of the catalyst. The third one is the H2TPR. You want to find the reduction temperature. And the fourth one would be the temperature program, CO2 TPD, to find the acidity and basicity of the catalyst. We then going for a catalytic evaluation via by reforming of methane. Later, when we have got the spent catalyst, we are going to characterize using TPO to see the amount of carbon deposited and the crystallite size, whether it increase or decrease, whether it's appear or disappear from the catalyst itself. Okay, and last but not least, we did some optimization study. So this is some of the steps to prepare the catalyst. We have first assigned the support. We do the sample preparation. We dissolve the active sites with the support. We do some ultrasonic radiation. We dry it and we calcine it at very high temperature. The calcination temperature will depend on the reduction temperature that you have obtained actually. So we have did some try and error before we actually come out as the temperature reduction of how much for the study. Sorry. Okay, this is the promoted catalyst steps whereby we have already got the copper monoxide catalyst. We are supporting it, or we are actually we would like to increase the performance of the catalyst by dissolving the ceria with the catalyst. The same method, we're still using the wet impregnation, ultrasonic wet impregnation method, and the same steps actually taken until the calcination process. We have prepared 15% Cu MnO2, and we have also prepared 3% Ce, 15% Cu and MnO2. Okay, so this is the rig that we have in our lab. We are using a fixed bed reactor for our system. This fixed bed reactor will be connected with all the gases, and we have a filter at the end of the outlet port so that the gases that being produced can be straight away collected and tested in GC-TCD, because you might experience that there will be some steam as well coming out from the gases. So having impurities within your gases will actually damage your GC itself. So we need to be very careful. If, let's say, we can see some bubbles of water inside the sampling bag, we need to retake the samples, or we need to improve the direct bag so that the gas that come out from the reactor will be only gas. Yeah. We are using fixed bed reactor. We are using a tubular pipe bag. That when you can see here, the catalyst will be packed in the middle of the reactor itself, and we are supporting it with a quartz wool so that the catalyst didn't move around. Otherwise, some of our reactor, we also have some basket, like a small basket inside the tube itself, so that the catalyst can sit inside the basket, and it won't go anywhere during the process. Yeah. These are the reaction conditions that we have. We are testing the temperature from 700 to 900, GHSV from 16 to 26, the pressure is 1, and the feed ratio of 0.2 to 0.1 to 1.0. Okay. These are the, as I mentioned to you, we did some optimization. Before we did this optimization, actually we need to do a two-factorial analysis or two-factorial screening so that a good range of has been selected for optimization. But since we have done methane reforming quite a lot with other catalysts, so we can actually predict. We didn't do any two-factorial screening because we can actually predict what will be the range, suitable range for the reaction to occur, what will be the suitable feed ratio and GHSV. So we play around with that range, then we come out with the one that we have insert in the design expert itself. Okay, so a bit on the results and discussion. The first part will be the characterization part, where we can see here there will be results on the total pore volume, average pore diameter, and the BET surface area. you can see that there will be a decrease of surface area when the CU is being added up to the catalyst and the CE is being added up to the catalyst. So it can be seen that the more you add up the other active sites, you will be experiencing a different or the reduction in terms of the BET surface area. So it actually indicating that there will be effective dispersion of metal on the catalyst surface, and there will be a very minimal blockage, as we can see that the total pore volume is not being affected much. Okay, sorry. From the XRD results, we can see that the presence of CeO2 actually giving some diluting effects, as we can see that the average crystallized size is being reduced in the promoted samples. And actually the function of the CeO2 actually is to help to isolate and prevent the agglomeration of CuO particles itself. So for XRD as well, we can see that there will be three chemicals or catalysts that are being tested: the support itself, the support with the active metals, and the support with the active metal plus the promoter. And we can see that the peak that we're supposed to see, the MnO2, the CEO, the CeO2 peak is there. And we can see that the intensity is being reduced as we add up the active sites, which is CU, and the promoter, which is the CeO2. Okay, this is the results on the reusability or reducibility of the catalyst via H2 TPR, where we can see that for H2 TPR, within the range of 300 to 600, you can see that there will be a peak that will be in blue color that correspond to the CU particles, reduction of CU particles on the surface. And there will be the second peak, which is from 350 to 700. This actually represents the decrease of fine dispersed CuO nanoparticles that indicate a significant interaction with MnO2. Okay, so sorry. Oops. So we can see that the general profile for both of them would be, because the first one, A, is the 15% CU without the promoter, and the B part would be the one with promoter. The trend itself will be unaffected by the addition of promoter. However, we can see that the presence of CE actually improved the dispersion of CuO, resulting the temperature rise approximately 23 degrees C for peak 1 and 12 degrees C for peak 2. Okay, so from this TPD also, we can see that the catalyst has been totally reduced at 520, and therefore we calcine the catalyst when we do the preparation of the catalyst, we calcine it at 600 degrees C. Okay. The second one is the CO2 TPD, whereby the CO2 TPD is actually giving you some information on the basicity and acidity of the catalyst. Mainly CO2 TPD is on the basicity sides. We can actually calculate the acidity, vice versa, but there will be some calculation that you need to actually do in order to get the acidity itself. You can see that the intensity of the promoted catalyst, which is the orange color, was higher compared to the blue color. And this increased intensity actually attributed to the addition of CO2 in the catalyst, and also suggest that the improved basicity properties can be seen on the promoted catalyst, which enhance the oxidation of the carbon deposition through CO2 gasification. So the purpose of us having the CEO2 is actually to provide the oxygen itself in the reaction, so that the catalyst can be, the carbon can be uplifted from the catalyst surface and making the catalyst remain active at longer duration time. So the stability of the catalyst will be better. Okay. This is the catalytic performance at different temperature. First is at different temperature. You can see that the range of the good temperature will be between 700 to 900. However, at 800, we can see that the conversion is declining. We can see 800 would be the one with the highest performance or highest conversion. The second figure is actually in, these are the same reaction, except that the one that they measure will be a different thing. The first graph, the one below the table, would be on CH4 conversion. The one on the right-hand side, on the top part, would be CO2 conversion. And the one on the right-hand side, on the bottom part, would be the H2CO ratio. Because this H2CO ratio, depending on the process that you want to have post-reaction, you definitely need to actually have a certain ratio so that it can be used to produce that particular intermediates. Different intermediates are going to have different syngas ratio that makes the process more efficient. Okay, so now we are looking at ANOVA, whereby you are having this p-values, f-values. I'm sure that the one that have been used RSM before, we are using CCD for this case. And we can see that the p-value, the model is considered to be significant as the p-value is below 0.05 and the f-value is higher. And we can see that for RSM model that we have produced, the conversion of CH4, which is the methane, is highly significant, indicated by this F value and P value less than 0.5. It also found that the feed ratio of CO2 also influence the CH4 conversion. Table 5 actually represent the ANOVA results for the CO2 conversion. And we can see that from the CO2 conversion, it can see that GHSV is actually play a very significant role in CO2 conversion compared to the table 4. It's different. In CO2 conversion, GHSV plays an important role, and it was proven by the results of the p-value itself. Okay. Table 6 actually shows you the H2CO ratio, whereby the model is considered to be significant. And we can see that from the findings, it shows that the ratio between H2CO increased dramatically with the enhanced soft feed ratio. We can actually say which one is better. It depends on what you want actually for your H2CO ratio. H2CO ratio will depend on the post reaction that will be happening after the syngas productions. Okay, we got a very nice flying map is here in our RSM, and we can see that the interaction between all three parameters is very good, and it obtained the highest peak as been seen by all the 3D surface plots inside this figure. And the first one, we can see that the effect of temperature, we can see that when the temperature increases, the conversion of CH4 and CO2 increases, and it giving the highest peak at 800 degrees C. However, we can see that there will be the decline beyond 800 that will be possibly attributed by the increase of carbon deposits on the catalyst surface that hinders the catalytic activity. Okay. On the effect of CO2 ratio, a similar trend was observed as well. And we can see that there will be increase in the CO2 ratio in the feed that increases the methane conversion. This might be due to the oxidizing properties of CO2, which actually positively influence the conversion process. Okay. On the effect of GHSV, there will be no substantial impact on the conversion. However, this GHSV actually exhibit the most significant impact on the CO2 conversion. This might be due to the shorter time contact between the catalyst and the reaction to interact, result in the low catalytic activity. So this is the table 8 actually shows you the optimum condition generated by the design expert, and we have actually run the experiments again to see the reliability of the results, and we found that the percent errors is quite small, and with that we are confident that the results coming out from the optimization is very good. This is some of the results for the spent catalyst, whereby we can see that with the presence of CE inside the catalyst, the carbon has been reduced a lot, and we can see that the one without the CE, without the promoter, you can get approximately 28% carbon deposition, whereby when you add the CE inside the catalyst, you are getting approximately 18.9%. Okay, so we can conclude that the presence of promoter actually reduced the carbon formation, which due to the introduction of CE that leads to the reduction in the crystallite size and decreasing the carbon deposition. So as a conclusion, we can say that the catalyst that we have obtained has been successfully synthesized and possible to actually give a very excellent performance of conversion, because there will be an excellent metal dispersion on the catalyst surface itself, leading to high syngas productions, and we have been able to reduce the carbon formation. This can be actually and improve later by modifying maybe the loading of the CE, or you can adjusting the ratio, because you are using a fixed condition for GHSV and for the ratio. We might want to play around with that to show that there will be possibly a higher reduction of carbon position can be achieved from the process. So from the optimization process, we have got the optimized condition, and it was proven by the experimental work that this optimized condition is valid and up to 95% confidence level. With that, I end the presentation. I'm taking about half an hour to present my work. Is there any question that you would like to ask?
Baik, terima kasih Prof. Sumaiya untuk presentasinya yang sangat bagus sekali berbicara tentang katalis.
Thank you.
Ya, berbicara tentang katalis dan bagaimana meningkatkan kualitas atau produktivitas dari syngas. Syngas ini sedikit tambahan memiliki banyak manfaat, tentu saja semoga bisa dapat diterapkan lebih lanjut di negara kita, Indonesia, menggunakan katalis copper ya, Prof, yang diembankan di mangan oxide ini, MnO2. Baik, saya membuka sesi pertanyaan. Untuk sesi pertama kepada dua penanya, saya persilahkan yang mau memberikan pertanyaan ataupun mau sedikit mencuri ilmu kepada Prof. Sumaiya, saya persilahkan. Saya persilahkan. Mari Prof. Reiner.
Terima kasih Pak Mesak. Thank you Professor Sumaiya. It was a outstanding research topics that you tried to overcome the greenhouse gases, methane issues. I'm not an expert in catalyst because I'm not engineering, chemical engineering, but I just want to know maybe the more ratio about the cerium and copper, the optimization of the more ratio of the cerium, Ce and Cu, cerium and copper.
Actually,
And then, and then the second one is any issues about the lifetime of the catalyst, because most catalysts, they just can be used just once and then to throw to the bins. We can regenerate them again. Maybe those two questions from me. Thank you, Professor Sumaiya.
thank you Pak Rina. Untuk catalyst ini, sebenarnya kita boleh ada soalan yang pertama, boleh ada combination between the normally that the one that we use in bulk would be the support. Kita pakai macam-macam jenis support sebelum ni. This is one of the support yang mungkin kita nak cuba test kerana normally people akan pakai alumina, lantana. So a very good support. That one can be considered a very good support. People always use that, silika sebagainya. Tetapi untuk ini kami cuba untuk menggunakan mangan oxide, melihat capability of mangan sendiri sebagai support. Tetapi kita boleh play around juga dengan amount of active site dan juga CE. Normally CE ataupun promoter yang kita pakai will be within a range of 1 to 5%. Tidak boleh terlampau banyak kerana dia akan block the surface area of the catalyst. Dan untuk nickel juga normally people akan opt daripada 1% kepada 20%. That would be the maximum amount of catalyst yang selalu kita guna untuk reformer. Okay. We can play around with that. We can also play around with buy support. Sometimes kita juga buat buy support, kita guna lantana dan alumina, kita juga ada buy metal sites which is cobalt dan nickel. So many things that you can play around to actually improve the performance of the catalyst. Second thing on the stability, ya betul, stability adalah yang paling penting kerana setiap kali selepas ujian kami kepada catalyst, kami akan membuat stability test selama 72 jam lah untuk melihat, kerana untuk membuat terlalu lama juga agak sukar kerana student juga tidak boleh berada terlalu lama di dalam lab dan juga rig itu sendiri tidak boleh mungkin sustain, tetapi kita juga precaution jugalah kerana alat-alat di dalam rig itu seperti mass flowmeter harganya beribu-ribu, berpuluh ribu maksudnya. So kita juga perlu menjaga kesihatan rig supaya kita masih boleh buat eksperimen. So the maximum that we have done is 72 hours and it's stable. It's still giving the same conversion after 72 hours. We might want to test more, but I am not confident with the time because to set up the rig itself is very, very expensive.
Thank you, Professor Sumaiya.
Okay, terima kasih menjawab soalan ya. Ada lagi soalan, Pak David?
Selanjutnya, Bapak David, saya persilahkan Bapak David untuk memberikan pertanyaan. Terima kasih.
All right, thank you, Prof. Sumaiya, but I'm not sure you have time. It's 9 already.
It's okay. I can squeeze 1 or 2 minutes more.
Okay, thank you. Short question. Did you write your own software for the model of surface what do you call it? The optimization part. So did you
Uh,
write your own program software for that?
that one is not my program. We are using a software, Design Expert. I'm not sure whether you have experience using that one or not. In that software itself, you can actually put the parameters that you like to monitor. For example, for my case, kita nak monitor yield dan juga kita nak monitor conversion. Okay, we put that as a response apa yang kita nak. Dan di dalam kolom yang lain kita akan perlu meletakkan apa range of eksperimen yang you nak buat, temperature range, ratio range ataupun GHSV you letak di situ. Dan sistem itu akan generate list of eksperimen yang you akan kena buat. Dan bila kita dia akan bagi like 20 eksperimen that you need to do. From that 20 eksperimen, you buat ikut yang telah dia listkan. Dia akan listkan apa temperature, apa ratio dan apa GHSV. You run the experiment. You masukkan result, yield dengan conversion. And then bila you run, bila you dah siap untuk 20 set eksperimen yang berbeza-beza condition, dia akan simulatekan supaya you dapat optimum condition. That will be the beauty of Design Expert. I'm not sure whether you have used it or not before, but in our country, we use it quite a lot to actually minimize our time to do experiment so that we don't have to test one by one. We don't have to do the temperature first and then we stick to the same condition for the rest and then we do the ratio and then we stick the... When you do like that, it's not going to be optimized. You're not getting an optimized condition. You can only get the optimized condition using softwares like Design Expert. There will be quite a number of software, but the one that I'm using currently is Design Expert. I know that there is some other software that you can use as well.
All right, thank you. Yeah, I do use I did what we call simplex optimization written by my supervisor. But in Indonesia, I don't think we should use this much. I think we are going to do it. Yeah.
Yeah, actually for Design Expert, you can use for any other experiment, extraction, reaction, anything that you want to have an optimum condition. We have done it for my case. I've done for my reaction, for my extraction process. I've done solid liquid extraction as well. I'm using Design Expert as well to maximize because your student for your final year project, right? They only have 2 semesters. So to test one by one is going to be tedious. So by Design Expert, they just generate 20 experiments. You just do that 20 experiments, you can get a very good graph like I did for the optimization.
Yeah, I agree. I mean, a univariate optimization is might be tedious and laborious.
Yeah. If let's say, maybe kalau lepas ni untuk mobility misalnya kan, ada student FYP yang ingin buat di sini, boleh send ke sini. Maksudnya kami boleh ajar lah cara nak buat. You can bring your data from your country. We can actually simulate here and do some experiment here. Later they can bring back to Undana and you can do papers, good papers with that. Sebab kami ada access software di sini untuk Design Expert tu memang ada lab yang boleh guna Design Expert lah.
Thank you so much, Prof. Sumaiya.
Okay.
Baik, terima kasih. Sebelumnya saya mau
Ada
mengucapkan
gabung,
selamat datang.
Pak Dekan ada gabung.
Selamat datang
Bisa
Prof.
Pak
Philip.
Dekan. Ada Prof.
Prof.
Philip.
Philip, apa khabar Pak Dekan?
Selamat, Prof.
Selamat.
Sumaiya.
Saya
Sumaiya,
mencari
apa kabar?
juga tadi. Mana Pak Philip ni?
Aduh, mohon maaf tadi saya masih ini ada ibadat hari Jumat ini, makanya saya tidak ini.
Baik.
Thank you very much.
Thank
For
you very
sharing
much for inviting
everything
as well.
for Department of Chemistry.
Ya, terima kasih.
Really appreciate Prof. Sumaiya.
InsyaAllah.
Ya. Semoga kita bisa ketemu lagi.
InsyaAllah bisa.
Amin.
Setiap hari saya melihat Labuan Bajau.
Iya, di Labuan.
Di Labuan Bajau ya.
Ya. Siap.
Terima kasih Pak Philip. Terima kasih buat semua dosen-dosen,
Terima
buat
kasih.
anak-anak.
Prof. Terima kasih.
Iya. Prof. Febri, mohon maaf, saya agak terlambat tadi masih jalan
Tidak
salin.
apa, Prof.
Ada
Tidak
acara.
apa, Prof.
gereja.
Silakan moderator,
Ya,
masih ada lagi
lanjut.
pertanyaan?
Baik, terima kasih. Mungkin masih ada lagi yang ingin ditanyakan. Saya berikan kesempatan satu orang penanya terakhir, karena mungkin Prof. Sumaiya memiliki kesibukan lainnya,
Kegiatan lain ya.
kegiatan
Ya,
lain. Saya persilakan satu penanya. Mungkin ada yang ingin bertanya, saya persilakan.
Moderator
Baik,
juga bisa tanya.
ya, baik. Kalau tidak ada yang bertanya, saya mau bertanya, Prof. Sumaiya yang saya hormati. Eh, Baik, Prof. Sebelumnya saya teringat berbicara tentang katalis ini, saya pernah melakukan sebuah penelitian bagaimana menghidrorengkah minyak nyamplung untuk menghasilkan biofuel, Prof. Jadi menggunakan katalis nikel, kobalt, molibdenum juga untuk diembankan pada gamma alumina sebagai pengemban atau promotor. Nah, Prof, di sini yang saya mau mungkin berguru sedikit, mungkin Prof bisa bagikan sedikit ilmu kepada kita semua, khususnya saya. Prof, waktu menghasilkan hasil itu memang koknya sudah rendah, tapi masih ada hasil samping seperti wax, lilin, Prof.
masih ada apa?
Hasil samping seperti lilin, wax, itu dia masih
Side product
tercampur.
lah.
Ya, produk samping.
Menghasilkan wax.
Ya, dia
Side
menghasilkan
product, right? Ya, side product.
side product, Prof.
Oh, daripada
Ya,
proses apa
Like
tadi tu?
wax.
hidrorengkah, hydrocracking, Prof.
Hydrocracking.
Ya, hydrocracking. Jadi menghasilkan wax. Nah, saya mungkin mohon saran dan ilmu dari Prof supaya ke depan kalau saya lakukan lagi mungkin bisa menurunkan wax-nya itu, lilinnya itu, Prof, jadi lebih rendah. Bapak Prof, saya persilahkan.
Sebab saya tidak pernah buat hydrocracking. So saya tidak takut juga nak explain sebab yang pernah saya buat adalah thermal cracking sahaja. To be honest, saya tak tahu juga macam mana nak menjawab soalan tu. Kerana dalam thermal cracking kami tidak ada experience penghasilan wax itu sendiri. Kerana mungkin ada reaction between the chain of the carbon itself bersama dengan air yang digunakan menyebabkan terjadinya wax itu. Saya rasa perlu dieksperimentasikan untuk saya lihat bagaimana untuk reduce the wax itself. Saya takut nak memberi jawapan, takut jawapan saya salah kerana saya juga tidak pernah membuatnya. Tapi boleh kita bicarakan selepas ini sekiranya nak berjumpa ataupun nak berdiskusi lanjut selepas sesi ini. Boleh kita tengok in detail lah sebab saya perlu baca kenapa terjadinya begitu. Kena ada sedikit penelitian dahulu sebelum saya memberikan jawapan. Takut tersalah nanti payah ni bawa ajaran
Tidak
sesat.
masalah. tidak
Baik, Prof.
masalah. Baik,
Nanti
Prof.
saya izin mungkin ada nanti nomor kontak Prof Sumaiya ada di saya. Siapa tahu Pak Mesak mau berdiskusi lebih lanjut.
Ya.
Siap, Prof. Terima kasih. Baik,
Terima kasih.
terima
Ya.
kasih banyak Prof Sumaiya untuk jawabannya. Saya kira kita sudah sampai di penghujung ya. Sudah 3 pertanyaan, kemudian materi yang sangat hebat sekali dari Prof Sumaiya ya.
Ya, insyaAllah. Nanti saya
Oke.
akan share dengan Bu Febri lah.
Siap, Prof.
Baik.
Nanti sekiranya ada yang untuk nak set up reformer di Undana, boleh kita kolaborasi bersama. Saya boleh ajarlah bagaimana untuk set up di sana. Sekiranya ada yang nak buat hidrogen lah, yang untuk fokus untuk renewable energy. Masih tidak ada saya rasa. Tidak ada lagi kan yang buat hidrogen di sana? Ke masih sudah ada yang buat hidrogen?
Belum ada lagi saya
Belum
kira.
ada. Ya.
Boleh kita set up satu grup yang buat hidrogen. Semua orang sedang looking towards hydrogen sekarang, alternative
Yeah.
fuel.
Ya.
Especially for energy.
Ya, boleh kita dah mula di Undana.
Ini Prof ada calon-calon S3 ini Prof, calon-calon
Ya.
doktor.
Kena datang belajar sini dulu. Lepas tu nanti bawa balik ilmu ke sana. Boleh
Ada
set up
3 orang Prof, ada 3 orang, ada Pak Mesak sendiri, ada Pak Marlon dan ada next mungkin Ibu Sinceng. Gitu.
Ya.
Masih
Boleh.
S3.
Saya boleh carikan supervisor. Sebab saya dekan kan, saya boleh. Saya boleh.
Dan memang semuanya physical chemistry, kimia fisik. Jadi mungkin
Kimia fisik.
cocok.
Ya, cocok.
Ini cocok.
Pasti
Ya.
cocok. Ya. Baik, saya terpaksa berundur dulu sebab dah ada orang tunggu saya dekat luar untuk
Baik,
bermesyuarat.
Oke, Pak Mesak, saya langsung ya, Pak
Ya, ya.
Mesak. Baik, yang saya hormati Prof. Sumaiya, Bapak Dekan, Prof. Filipi Deresare yang bersama-sama dengan kita hari ini, Bapak Ibu dosen, kami mengucapkan terima kasih, dan moderator, dan adik-adik mahasiswa, kami mengucapkan terima kasih kepada Prof. Sumaiya untuk ilmunya yang luar biasa hari ini terkait katalis, dan ke depan ada Bapak Ibu dosen yang biasa riset di katalis, dan pengembangannya itu biasanya mereka pakai zeolit alam dari NTT yang memang katanya karakteristik produk apa lokal dari NTT. Jadi mungkin ke depan seperti Ibu Hermania, Ibu Bibiana mungkin nanti bisa berkomunikasi dengan Prof. Sumaiya untuk
Bisa.
pengembangan katalis juga. Saya pikir banyak banyak teman yang juga punya arah riset ke arah pengembangan katalis.
Ya,
Jadi saya
kami juga
mengucapkan
sedang buat untuk SBA 15, kita memang
ya,
KCC, kita
siap.
memang tengoklah untuk support.
Ya. Nanti kalau bagaimana Prof kita berkomunikasi mau buat grup atau bagaimana nanti kita buat kita setting pertemuan online lagi Prof di
Ya,
luar
betul,
sini.
boleh. Ya. Nanti
Terima
Bu
kasih.
Febri arrange lah, ya.
Ya, terima kasih untuk kehadiran Prof Sumaiya dan Bapak Ibu semua untuk MRT pagi hari ini, dan sebagai koordinator program studi kimia, saya menutup dengan resmi kegiatan kita pada pagi hari ini. Terima kasih semuanya. Tuhan
Terima
memberkati
kasih.
kita.
Terima
Ya.
Terima
kasih.
kasih.
Terima kasih Prof Sumaiya.
Ya.
Siap.
Ya.
Pak Mesak masih mute, Pak.
Ibu Korpro, kami menunggu di ruang meeting.
Saya di rumah. Dan mungkin saya agak sedikit terlambat juga karena saya gigi sakit. Jadi saya masih ini dulu.
Oke, siap.
Saya pasti terlambat. Baik, terima kasih Bapak
Baik,
Ibu.
terima kasih.
Kita rapat lab.
Terima kasih.
Terima kasih
Terima
Prof.
kasih
Terima
banyak,
kasih.
Prof. Terima
Terima
kasih.
kasih, Prof.
Ya,
Terima kasih.
Terima kasih Pak Mesak, teman-teman
Terima
Bapak
kasih.
Ibu.
terima kasih Prof Renner.